It's running in the background. Yes, you got your light. One second, I just want to double check that you're actually in screen. See that? That's right. Okay, so you're going to be stuck there?
Yes, yeah. Yes, okay, that's why I moved it around. Because we can put the slides in later. As long as we get the cue, that's it. I'll try and stay here.
Okay, so that's good. Okay, if I can just ask everyone to take their seat. Jenny, is there any way to turn off the music?
I thought it was on. I turned it on. It's still on?
We can still hear it.
Oh, all right. Well, I haven't turned it on. The camera's in the corner. Just pull the plug out.
Okay, everyone. I'd like you to join me in welcoming our speaker for this evening, Frank Johnson, who is a fellow of the IET and a member of the IET Council, and has come all the way from Ottawa to speak to us tonight. He has a long, varied history in a whole bunch of industries, especially within medical engineering. And I will hand it across to you to take it from there.
All right, thank you. Pleasure to be here. Actually, Rose had offered to tell you a few nutty jokes before I started, but I pointed out with a name like mine, I can make more than enough noise anyway. So we skipped that bit. But for those of you who are not quite sure what's coming off, and I'm not sure whether you can see, if the top line is not clear, hands up anybody who thinks the top line is not clear. Okay, well, you've had too much wine, so we'll expect you to fall asleep. A lot of us are a little bit depressed at the moment because of recent political events. And I thought I would tell you a short story about a Canadian philosopher just to cheer you up. George Grant was often asked why he was so pessimistic. And he said to them, well, really, I'm not pessimistic at all. I quite firmly believe that this world will be wiped out and we'll get a new heaven and a new earth. I'm very optimistic about that. So with that level of optimism, I'm going to light the blue touch paper and begin my Christmas lecture. Now, you may wonder how anybody would have enough audacity to talk about the next 50 years of medical engineering. And the answer is quite simple. In fact, it's an identical answer. Sorry, sir.
Did you ask the professional engineers of Ontario if you were allowed to call medical engineering?
I am a professional engineer, thank you. So I am entitled, therefore, I believe, to stand up and talk about engineering. Any more interruptions like that, and we're going to go off into a different tangent. I was asked when we bought a pub by the interviewer on the CBC. He said, well, you're an engineer, you know nothing about running a pub. And I said, Really? I'm an engineer. I therefore spend most of my life doing things I know nothing about. And so where we're going in 50 years, I think is well within my competence, sir. So I'll accept no further harangue on that point. What I was going to try and do was a simple mathematical trick. If you take 2 points on a line, everybody knows that you can carry that line on as far as you wish. And just in case I have some mathematical purists here, I'm going to go back to the middle of the 1860s. So we'll have 3 points on this line. And as my former supervisor knows, Professor Kuloff, if you've got 3 points on the line, you can do anything with it. Now, I want to mention in the history of medical engineering, as far as I'm concerned, it started in 1963, and this illustrates the importance of heroes. In 1963, a chap called Leslie Kay came to my grammar school, as we called it then, a high school for those people here, and he talked about the application of ultrasound to a mobility aid for the blind, and I thought this was fantastic, because as an amateur radio enthusiast, as I was then, it gave me something to do which was useful. And I decided, I remember the day that he spoke, and I remember the correspondence we had afterwards. I decided then that I would work into medical engineering as an application of my engineering. And preparing this talk, I thought, well, I'll just see where this has all got to. And sure enough, on the web, you can find a pair of ultrasound glasses, there's the ultrasound transducers, which are designed to give mobility for those people with reduced sight. They overcome one of the shortcomings which Leslie Kay had not, and that is they didn't put the sound into the ears. They put a vibration at the back of the ears, which meant that the blind people do not lose the other major sensory channel which they have for navigation, which is auditory. So, the importance of heroes. You never know when you give a talk what you're going to do to people, just as I don't tonight. I have another hero which I want to confess about, and that's the importance of this candle. Michael Faraday used to give Christmas lectures, and I frightened Rose by showing her the volume of the Christmas lectures, which I've been reading and preparing for tonight. He would cheerfully speak for a good solid hour. And there's 4 of them in here, so you can see what you've got in front of you. But what he did was absolutely brilliant. He would take something as simple as this, and then say, you sir, why do you think that candle won't work in space? You're hoping to go to the moon next week, maybe next year. We've got the postcards ready for you. It'll take you a little bit of time to get there. Why is it, sir, that candle won't work? Or will it? Perhaps it will. What is your answer?
No atmosphere.
No atmosphere. Well, actually, I'm hoping that we take a little bit with us.
No gravity.
No gravity. So why is it that gravity is such a problem for a candle?
It's presuming that hot air will rise due to gravitational load, therefore bringing more oxygen.
The hot air rises, indeed. And in fact, if I move this over here, you can see the hot air rising. And if I speak for long enough, you'll see a lot of hot air rising. In fact, 1861, page, where is it? That's the next slide. Sorry, I've got the answer right here. A little bit further. Here we are. 1861 in this book, in page 10, he's got that answer. He used the candle as an illustration to get the children to think about why things would work here and don't work in space. Or indeed, he went on to develop this as an illustration of the chemical processes going on. There's another reason why it won't work in space, and that is that the wax, which is melting in a nice pool, would also float away. And so that beautiful cup which you see around it and stopping wax pouring out wouldn't fall, etc., etc. And his overriding point was, we have come here to be philosophers and hope that you always remember that whatever a result happens in any experiment, you say, what's going on and why does this occur? And this illustrated what Faraday did throughout his life. And I'm not sure that I want to pretend that I'm a Michael Faraday, but it is a simple guiding principle which is worth carrying with you. Now, I was going to have a glass of water, well, a glass of ice here, and place it on top of the candle. However, I'm told by the hotel that if I break the glass, I'll have to pay for it. And they didn't provide me with very much ice anyway. But I would like you to do a mental experiment of imagining what would happen if you have a glass of ice, which you've just taken out of the freezer, you place it on a candle, and what would happen to the temperature. And you can do that while you're thinking about other things and possibly even listening. And incidentally, I'm going to turn off the Wi-Fi, so you can carry on with that experiment now. What I'm going to do for the rest of this evening, or at least the majority of it, is talk about a few points in the last 50 years of working. And at U of T in 1968, I already had an undergraduate degree in electronics. And so, of course, they thought I was well qualified, therefore, to do a master's degree in gynecology. After 2 years of that, the gynecologist pointed out that really I wasn't doing all that well. So they moved me into neurophysiology. And 3 years of that under Hans Kunoff's able supervision, with a lot of help from his friends, I was gently moved on. And so I went into orthopedics. And then we're going to get into anesthesia. If you're still awake, we may actually have a look at a bit of sleep apnea. And if we're not, we can all study the neighbour's sleep apnea. So that's the sort of rough time scale. You'll see that little picture come up. You'll know where you are. If you do happen to wake up and the thing's all filled up, well, you know you've missed a few bits. So, detection of ovulation. In 1970, I met one of Hans's colleagues, Richard Cobbold, and a lovely obstetrician, actually Al was it, but the first initial was C, and he was at the St Michael's Hospital, and we worked together looking at telemetric methods of detecting ovulation. Now, why would we be interested in that? Why would St Michael's Hospital, which happens to be a Catholic hospital, be interested in it? Well, it isn't any of those conjunctions. It's because the point of ovulation is obviously the central point in a reproductive cycle. It is controlled to some degree by the rise in we're going to get this right, the luteinizing hormone, which about 36 hours peaks, 36 hours before the egg is released from an ovary. In those days, the only thing you could do to get this timing correct was to take samples and do a fairly tedious laboratory analysis. They said it would be really nice if we could measure something else. People have been doing it. They looked at various things, and in those days, measurement of body temperature was probably the most significant or simple way of doing it as an indirect way. What's interesting, and this is where the 50 years and the extrapolation comes in, what's interesting is that if you look on the web today, you'll find these kinds of graphs being produced. And sure enough, the basal temperature does change by about 1/10 of a degree. No, not by 1/10, it's by more than that, by 1/2 a degree. And sure enough, occasionally, you do get a dip just before the point of ovulation that you're looking for. The hesitation which any engineer will have is if you're coming along here and this is the only data, these are the only data which you can see, you know, is that a dip or was that the dip you're looking for, and so on. You really can't be sure until afterwards. Well, what has happened in the meantime, that was not a joke. What has happened in the last 50 years or 40 years or so is that we've become very clever at measuring the actual hormones in urine, and we've done that by development of a technique which I find quite fascinating called monoclonal antibodies, and it's used across the spectrum of analysis of body fluids, whether it's blood or urine or anything. And the way it works is that if you want to detect this yellow and blue thing, you find a green thing which attracts it. And you hope that the green thing doesn't attract anything else. And if you coat a dipstick with green stuff, and then dip it into something which has got some of these yellow and blue things, then they stick to the green stuff, and you can pull that out, and you've got a nice layer which you can then detect. And there's a whole range of tests which are done that way. And this was one innovation. But the question still is whether you can do the, whether you can improve that. I mean, that's very good if you're in the business of selling those dipsticks. And if you sell those dipsticks at $1 a time, or whatever it is that they charge for them, I think it's about that, you can clearly make a lot of money. The only snag is that the window that you're looking for, remember, is that 36 hours. And if you use that once a day, you know, you've got a sampling problem. So can you go back to the time series of some of these other secondary parameters and look at that? And temperature is an obvious one. And analysis of time series is something which we're very good at these days. We don't have to have jerky things on the graph because we can have a smoother pattern. A lot of that noise is coming from poor sampling. And of course, we're all carrying a wonderful pack of sensors. So why don't we add that and have other sensors being put into this? And in fact, of course, you can now go onto the web and you can get the application that you've been looking for and have a precise graph on your iPhone watch. And as I said, comes a new meaning to the idea of carrying your heart on your sleeve. As I said, gynecology wasn't my field. I was moved swiftly on into neurophysiology. So let's do that tonight. I went to my old office today, and it reminded me of the school days. This is, there we are, the crest of the engineering students, club, or whatever it's called. What's significant is that I didn't belong to that, but they had a band called the Lady Godiva Memorial Band. I happened to come from a place near Coventry, so I knew all about Lady Godiva. And this band practiced every Thursday lunchtime right outside my office window, so it's imprinted in my mind. And this is where I had the pleasure of working closely with Hans Kunoff, who is sitting at the back and has been a great influence on a lot of things that I've done. And that's really when I sort of developed my ambition in life, as the school people did. English was never my first language, as you can see. So, neurophysiology. I wasn't allowed to look at, sorry, that skipped twice, doesn't it? Yeah. I wasn't allowed to look at the real part of the brain, the bit that does all the thinking. They said, no, Johnson, you've got to concentrate on what controls movement. And this is the cerebellum. And for those of you who are not familiar with what a brain looks like, there's a bit down here which is the primitive part, which seems to control our movements. And there's a bit up here which is all the clever part of deciding what to do in terms of where it's going. This part appears to work like something very much like a computer. And in fact, if you look at the anatomy of the cerebellum, you find something beautifully ordered. There are many things coming in. They're called mossy fibers. They sort of pass across one set of little green things, or not little green men, but little green cells, and they turn into these parallel fibers, running all the way around the surface of the cerebellar cortex. And then there are massive cells which seem to interface with all these parallel cells and produce an output. And it's tantalizingly like a computer and beautifully organized. And it is the model of what is used in neural networks, because each of these interfaces, the synapses, can change their influence. They can be modified in their weights. When you're learning how to play the piano, you will be training these synapses into the whole sequence of movements. And so it's an attractive place to start to look at how the brain works. And the other interesting thing is that the brain, that part of the brain, takes a massive input from the sensors in various muscles and joints and so forth. And when you look closely at these sensors, and the muscles are full of stretch sensors within the muscles and also at the end in the tendons themselves, when you look at them, they work in a very poor way in the sense of any engineering. They will fire and get fed up with the idea. Sometimes they fire quickly and then just get bored after a few milliseconds. Sometimes they don't even want to fire at all in any sensible place. And somehow the brain manages to put all of this together. I would have said that these are non-linear perfunctory sensors. It's a whole class of sensors which hasn't been invented yet, but that's my name for them. The other thing on this drawing is that it shows the spinal reflex circuit. We know that there are synapses within the spinal cord which are responsible for things like simple reflex. So if you tap a tendon either on the arm or on the leg, you will get a jerk in response. That's the spinal cord operating. But what I was interested in was what happens in the cerebellum. Now, what is curious about the cerebellum is a couple of things. One is that if you put a lot of these sensors in parallel, rather non-linear and fairly pathetic, very strangely, by the time you get to the cerebellum, the response is actually linear. And the reason is, according to my theory, that if you have a lot of sensors running in parallel, which are randomly selected and behaving in a stochastic manner, then adding them all up and you actually get a linear output. And that was a surprising result, number one. That's half of what I think I got the thesis for. The other odd thing, well, before we move on from that, you will have noticed that those the sensors are either on or off. They're sending out pulse trains. And this is completely unlike most of the sensors which we are familiar with in engineering. They tend to be linear. Or if you have a digital output, it will be a digital output which has multiple bits, 16 bits or whatever. They are single bit, D to A to D, sorry. Knowles, the microphone people, have brought out a single bit microphone. It works very much the same way. The higher the pressure, the sound pressure, in this case the lower the pulse rate, and as the sound pressure goes down, it will change. Now it looks as if their graph suggests a slightly different relationship, but the point is it's a single bit A to D. So the concept of using the same kind of sensor that you have found in the body is now turning up in sensors for the Internet of Things. It's a good example of what you might call biomimicry, or a good example of translation from one field to another, sort of lateral thinking or lateral engineering. And the other surprising result about the way the brain is working is that it really gets quite overwhelmed by a mass of data, to such an extent that if you pull a muscle or pull the sensors and then try and pull it again, the brain is not the slightest bit interested in it, even at the cerebellum level. And it isn't until around about 100 milliseconds later that the brain actually comes back online. So it appears that it goes away for a period of about 100 milliseconds, does a bit of thinking by itself, ignores what's going on outside, and then comes back and say, right, what's happening now? And you can test that with the same pack of sensors. And here's another experiment to have a look at. And what I'd like you to think of is turning on your seismometer app, which you've all got, of course, in your iPhone. It has a 3-axis accelerometer, and turn that on. Now, may I have another volunteer just to try this out? So, would you like to volunteer? Yeah. It won't hurt you, but I'd like you to stand up. Okay. All right. Now, I'd like you to put your hand out like that. All right. Now, I don't want you to hold it too hard, but I want you to, I'm going to put this battery in your hand. Yeah, okay. All right. I'll make sure you don't drop it. Okay. But I want you to close your eyes. And what I want you to do is, when the battery is dropped into your hand, I just want you to bring your hand back up to where it is. All right? Okay. Yeah, something like that. Yes. Okay. Try that again. So I think you were trying hard there. Yeah. All right. Okay. All right. Thank you. Very good. Thanks very much. If you do that and under repeated circumstances and measure the acceleration, which you can with this, what you get is this. And I only did this once, and I did it on myself, so it's not really fair. However, you can repeat this experiment. If you drop the weight here, what happened was there was an initial jerk because your spinal reflex, the weight just dropped on my hand. But then there was a long gap where nothing very much happens, and you start to drop. And then it appears to be that the muscle starts to contract and starts to bring the hand back up, and eventually you come back, and you can repeat this many times. You actually see it quite clearly on the acceleration. There's minus 1g, which is what your hand is seeing all the time. There's a little bit of a jerk as you, actually that's the spinal reflex jerk right there. But at this point, you've got nothing happening. The acceleration of the hand was 0. You're actually free falling for about 100 milliseconds. Then there's a big impulse, and then actually there's another impulse here. In other words, what you're seeing is that cerebellar action working on a clock speed of around about 10 per second. So we've got a clock rate of about a tenth of a second. We've got massive parallel sensors which appear to linearize things out. There's a lot of computing going on, even in the cerebellum. We've got all these Purkinje cells with masses of parallel fibers. And because of this very low clock rate, very probably what the brain is doing, the cerebellum is doing, is saying, a battery is just deployed on my hand. I'll think about that for a moment. And then it provides a calculation and comes back about a tenth of a second. And it's sort of predictive optimal control. That's a very simple conclusion. There are a number of people around who say, well, if you have a big enough computer, you can replicate what the brain is doing because it's just a mechanistic system. I'd like to just look at that for a moment as we try and track the trajectory of where brain research might be going. But before we do, I'd just like to return to our thought experiment. I asked you to take a glass of ice and warm it up and measure the temperature. How many of you arrived at this temperature graph? Exactly. So, as the ice warms up, for those of you who forgot about the experiment, as the ice warms up, it will start to melt and we'll get water and ice. And there'll be a period of time where there is water and ice together, the temperature stays about the same, 0, and then all of the ice is melted. It then warms up to boiling. There's another period of time where nothing much happens in temperature as the latent heat of evaporation kicks in. And then you get the temperature rising again. You'll get that heating only if you've got a closed system and you want to make a steam engine, which is not what we're going to do tonight. Now, my point of putting this on was that in the 1800s, all that people had was Newtonian physics. In fact, in the 1800s, well, in the 1700s, this wonderful substance called phlogiston was invented to try and cope with the problem of Newtonian physics in how water behaves when it melts. This was replaced with a caloric theory, which was still unsatisfactory, and it was the combined efforts of people like Joule and Faraday that actually put a proper understanding of this, of thermodynamics. And why have I gone off onto this, apart from wanting to mention Faraday's name again? Well, I mean, one possible application, of course, is that you might all be faced with the problem of how to prepare a turkey for a Christmas dinner, as well as Thanksgiving dinner, and the solution of having ham instead of turkey is not necessarily the one we wanted. The only possibility, unfortunately, is just to wait for a very long time. That's one application. The other real application is that you can't apply Newtonian mechanics to a beaker of ice and water. You have to think of something slightly clever. So if you're going to talk to somebody who wants to apply Newtonian mechanics and predictive theories to the brain, just hesitate a bit, think about the ice. There are, just to give you a few numbers, something like 86 billion neurons in the brain, and probably 100 trillion connections. But I went to see a lecture last year by Roger Penrose. How many people remember Roger Penrose? Anybody remember Roger Penrose? I got one. And then about 2, 3. All right. Famous Oxford mathematician, published things like The Emperor's New Mind. He's in his late 80s, I think, and decided to give a lecture which was to a packed audience on consciousness and the laws of physics. And I've typed out the key sense conscious thought processes are the result of non-computational physical actions. But this requires going beyond the present day physics. These are his actual slides, or well, these are photographs of his actual slides. He did assure us as he was drinking his water at the podium that he had used waterproof ink to do them. He said that was a consequence of a previous event, another lecture where he hadn't used waterproof ink. And that was just the introduction. He then went on to more and more quantum physics and mathematics. The only thing on this slide which I understood was that if a billiard ball falls up the table, then it's in free fall and you have zero gravity, a zero gravitational field on that ball. His main point was there were mechanisms which could be happening within individual synapses, which may be related to quantum physics. Now, if you want to see raging discussion, go and look up the orchestrated objective reduction theory on Wikipedia, or quantum physics in the brain. A lot of discussion going on right now about how the brain actually works. The summary for you is, each neuron may be a quantum computer, in which case we've got something like 86 billion of them. The biggest supercomputer we've made so far is 100,000 parallel computers. We've got quite a way to go, even though this is only operating at a clock rate of a tenth of a hertz. Yeah, 10 hertz, sorry. So a lot of interesting stuff going on there. And I think the next 50 years is going to be fascinating in that entire field. But let's move on swiftly into something that does use Newtonian physics and Newtonian mechanics. I met another great influence, Professor Wall. The one thing which I remember Professor Wall telling me over and over again was, Johnson, if you can't pick up your 35mm slide and read off the text, that slide has got too much text on it. And I have tried to spend the remaining period of my career trying to teach other engineers that if you can't read it on that screen, you'll never have a slide which you can read right at the back of the room. In 1980, we were very curious, not just curious, but very concerned that artificial joints like this, for the hip and the knee, were made of more or less the same materials, you know, titanium and high molecular weight polyethylene. And in those days, the average life of a hip was about 12 to 15 years, somewhere in that range. And the average life of a knee was somewhere around about 4 to 6 years. I do not know what the current statistics are. It would be interesting to find out. It depends on who what joints are being used and all kinds of other factors. One of the possibilities, we thought, was that the knee joint was taking more load than the hip joint. That's a simple way of saying, well, it's going to wear out sooner. Unfortunately, if you apply Newtonian mechanics to what's going on in these joints, you actually find that the hip joint takes at least twice the load of the knee joint in terms of pure vertical load. And in fact, it's only when you start to look at other moments in the knee that you begin to realize where the problem lies. And we studied several hundred people walking over a force platform, very carefully measuring the angle of their knee in the coronal plane, in other words, looking at it from the front. And a little bit of thought shows that as you walk, you are, of course, transferring load and moving the rest of your body around. And what's happening is that you're putting a lot of load actually on the medial side of the knee. And that's what you see on this graph, is the excessive load on the medial side. How does that work out in terms of the knee joint itself? Well, what happens is, of course, that this medial load can cause a collapse. Now you can see that collapse in both sides of the knee, depending on what the history is. And I don't know what the history of that particular knee is. But one of the challenges is that if you try to correct that by saying, we've got a bigger gap here, obviously what we need to do is put a bigger piece of plastic over here, we'll get our 3D printer, we'll print a piece in the operating theatre and we'll fill up the gap. That, unfortunately, will not solve the problem. And the problem in this picture, where in a normal knee, if you draw a line vertically between the center of the hip and it falls straight through the center of the knee and the center of the ankle, that is a good force alignment. If you have done a reconstruction and you've got this force one side or the other, then the load on the knee is going to be imbalanced. And that appears to be what was causing the trouble. And that was applied in two ways. One is we realized that we needed to be accurate to within 2 degrees. And you have to remember that orthopedic surgery is basically about taking a 2x4 and taking a saw and cutting it off absolutely square. And if you think you can do that, then that's the test that we gave you if you were an orthopedic intern coming in for a job in Nottingham in the 80s. Here's a 2x4, here's a saw, and I cut it off square. Well, of course, not very many people passed, and we needed a few more orthopedic surgeons. So we actually decided to apply a bit of engineering, and we made jigs to do this correctly. But the jigs had to take account of the alignment of the whole knee. And that was an advance. Now, as I said, I don't know what the current state of that is. I'm alarmed to find that people are suggesting using 3D printing, because that seems to be going the wrong direction. I suspect that over the next 50 years, we're going to see a lot of development, both in materials and mechanics, and the study of movement, and the techniques used in surgery. I'm moving on, if you're coming back to life. We're nearly on the fifth quadrant of the fourth quadrant of 5. Counting has never been my strong point. At the same time as doing all these orthopedic examinations, I had a look at some work done by now Professor Harrison, who's an anaesthetist. He said, look, anesthesia is really quite a sleep-inducing sort of occupation. Is there any way of automating it? And I said, well, clearly this is something we can use artificial intelligence for. And in those days, there wasn't very much artificial intelligence being applied. There were a few projects. The maxim project from Stanford was very famous. They were using that to recognize bacterial infections. They had great concerns, even in those days, of who was going to be responsible if you made the wrong diagnosis. So we ignored all this concern, and we simply said, well, let's see what we can do with anesthetics. Anesthetics is basically a matter of taking 5 things on the input side: urgency, the age, the medical history, the surgery, and the drug history of the patient, and turning that into a regimen, starting with preparing the patient, a bit of pre-med, induction, keeping them asleep, bringing them back out of it, and sorting out any drug interactions. Simple. You add then all the possibilities. You either need it done quickly, or you don't need it done very quickly, or somewhere in between. You can divide the age into 9 bands. The medical history is a bit complicated, as is the surgery. In those days, drug history was really quite a simple thing. There were 31 possibilities. And we had this slew of different outcomes, depending on where people were going. Even with that simple number, and you can do that calculation quite quickly, you get to at least 30 million, if not many, many more possible combinations, because you can have multiple combinations of history and so forth. And we produced an automaton that would actually give you all the anesthesia procedures, the regimen that was necessary. But then we sat back and said, well, it's going to take us something like 46 million years to work through this at the rate of 1 per second, even if Michael Harrison could keep his concentration up for that length of time just to check it out. And so a heuristic machine was clearly appropriate. Now, this was long before the days of deep thought and data mining, etc., which we have understood now can be done. We were trying to apply trained anesthesia practice to the problem. The approach which Google would take now is to say, well, forget any training, we'll just put up a machine and we'll let it sort through as many history of cases as we can and let it train itself. You've still got some of the same problems. It gave Professor Harrison a life work. He's still working on that. He emigrated to New Zealand. I'm not sure whether that was to get as far away as possible from me, but he did carry on with that. He met with a lot of derision from the Royal College of Anaesthetists at the time. Whole discussion is carrying on and will be carrying on for a long time. When you see the phrase 50 years to go, that's the clue that we're going to move on to another quadrant of 5-point star. The two Suskins, Richard and Daniel, the father and son, produced this great book on the future of the professions. If you're interested in this field, it's a good starting book to read. And this is clearly an area which is going to be heavily looked at in the next few years. Richard Susskind is a lawyer, and his son is an information technologist expert. But there's a lot of other work going on in this field, as you well know. So, part of my line is that there's going to be a lot of effort in this area. We are up to the last point, and I'm actually holding the device in my hand. So if we're all gently snoring away by now, I want to talk about sleep apnea, and this is actually right up to date. And the issue here is that the number of people who are suffering from sleep apnea is rising. The severity of sleep apnea is becoming better recognized. And in the UK at the moment, if you have an accident and it can be shown to be caused by drowsiness, you will lose the same number of demerit points as you would have done if it was caused by alcohol. So it's treated in the same way. If you go to hospital and ask for a sleep study, they will try and put this amount of apparatus on you and then say, well, now go over to that bed which is sitting in the corridor because we haven't got very many, and I want you to have a good night's sleep. So what we did was to say, well, look, this thing has got an accelerometer in it, which is a 3-axis accelerometer. It's actually got a pressure transducer in it, which is sensitive enough to tell me whether my phone is here or on the floor. Why can't we make that into a sleep apnea monitor? And then you can stick that on the chest about here with a couple of ECG electrodes, not because we want to measure the ECG, but because we can buy them very cheaply and they're completely safe to use. And then we can do the same monitoring. And also, if we use the technology in the phone, which we have a lot of, we can do some clever things about the data. Now, the first question is, will it actually work? And this is Cheyne-Stokes breathing, where you sort of breathe and then you slow down and then you suddenly snort and you come back to life, and so on. It can be done, and it can work with an accelerometer of the accuracy which a phone has got in it. It also allows you, and that's a simple way of doing it, also allows you to put sensors through Bluetooth into a phone and then transmit it off to the cloud. And I think the next step is obviously that you have the physician sitting over here reviewing the data which is seen in the cloud, never has to see the patient, simply types out the report, sends it back, and the patient stays at home, which is a big advantage. There are snags, and you hit these snags as soon as you try and do anything within an organisation like the National Health Service in the UK, which you would think was fairly straightforward because they're uniform. there's a little bit of security and stability which you need from the sensors via Bluetooth to the initial interface, which is the phone on the table. There's a bit more of a protocol question about putting it onto the internet without making it too broadcast. There's a lot more questions about how you get all that data down to a secure server and get it into the NHS and then bring it together for the physician to use. Each step along the way requires secure data. I was talking to a company in Ottawa that is making novel methods for security and saying, well, why can't we apply this? And it's very interesting. They have been around to several major government purchasers and said that in every case, when they've been to a big government department, they've always wanted to have a back door into the security system. So I think in the next 50 years, we're going to see a lot of thought about that. Let's return to our candle and to Michael Faraday and see something which actually hasn't changed very much. This is Michael Faraday's Royal Institution. He used to live somewhere on the top floor, and he wanted to get somewhere. He walked out and found a horse. This is the Royal Institution that I visited not so long ago. It really hasn't changed that much. It is perfectly possible, of course. It's been bombed and rebuilt, but that's another point. What is really interesting is that in the basement are all the instruments that Faraday used to use. Not the instruments, but the experimental apparatus that he had. And there's this famous comment, and I think it's based on this one, by Gladstone. So, that's very nice, Mr. Faraday. What's the use of this? Well, I said, well, I don't really know, but I'm sure you'll find a way to tax it. David and I actually went around the world showing off this photograph of Michael Faraday with an exploding cigar. Michael Faraday claimed it's a magnet. This is Faraday in his workshop in the basement from a contemporary etching. This is the actual place that they've reconstructed. The shelves don't quite look the same. I'm sure that cat box wasn't there in Faraday's time, but a lot of the apparatus was. And I'd like to move to one final experiment. This behind the glass wall were these bits of equipment, and you can recognize this as the compass needle. There is a battery. I think it's a 50-plate battery. And I just happened to have brought a piece of wire and a compass and a battery. And I'd like one more volunteer to hold the wire for me and then tell everybody what happened. Rose, it's about time you did something for this experiment. All you have to do is hold the wire there, all right? And don't burn yourself on the candle, please.
Okay.
Now, just because you're an engineer and you know what's going to happen, just pretend it's a real experiment and you don't know what's going to happen, all right? Okay? Now, would you tell everybody what happened? Or you didn't watch? That.
Changes the needle.
It moved the needle, and let's suppose it was like this, and we're passing the current through there. Which way does the needle go for the benefit of everybody else that didn't see it? You can let it go now. That's all I wanted. Which way did the needle go? And where did it end up?
I don't think your thing is pointing there.
You don't think I'm calibrated properly?
No.
Would you agree that the needle ended up pointing at right angles to the wire?
Yes.
Yes. That's all I really wanted to get out of that. Thank you. That was one of Faraday's most remarkable observations, somewhere around about 1838, 1840. And it led him to the development of the Faraday-Maxwell equation, effectively. I mean, Maxwell developed an equation, but this idea that the field was at right angles to the flux. And it's the last comment I want to make about the breakdown of Newtonian physics. You cannot explain that on anything that comes from Newtonian physics, even if you wanted to. But it also provides a little segue which goes straight into another part of my career. One of the bits of apparatus which Michael Faraday left behind and lovingly preserved by the Royal Society, I think the real piece was actually put on a velvet cushion at one point, was this toroid. And the toroid had a couple of windings. If you want to see the way it was done, we've got his diaries still preserved. If you look at that and then look at this, if you take two of those toroids and put them somewhere close together, you make effectively a sort of a double transformer. And this single winding can either be a piece of wire which goes through it, or it could be salt water. And in fact, Faraday would recognize this sensor for measuring the amount of conductivity of the salt water. And if you know what the temperature is as well, you can work out what the salt content is. And we have applied that, to produce a very accurate, one of the world's most accurate sensors of conductivity of salt water. The alternative is that you do it with a 4-electrode bridge. And anybody who's used a 4-electrode bridge will know that you have immense problems with it. And it can get dirty, all kinds of things can go wrong with it. This can be used without any contact with the water at all. And we produced a foundation paper only 6 years ago on the performance of that, in which we showed that it was the best conductivity sensor. Michael Faraday would have loved it. 160 years later, we find that there's nothing new under the sun. He reminds us to consider the results of the simplest experiment and don't throw all his apparatus away. I was hearing Hans saying how when he had to move office at the university, he didn't have space for all the apparatus which he collected over the years for different experiments. Obviously, your name is not Faraday, sir. And always be ready to move into other fields and think of applying things with other fields. So I want to begin, I want to end more or less where I began. Now, you may wonder why I brought a piece of Lego here. And very interesting that, oops, going too far. No. Yeah. Lego recently brought out something they call Mindstorms, which is Lego robotics. It has an armed core. I won't go through all its features, but it's a nice piece of kit. The important thing is it will control 4 motors using I2C connectors, and it will take 4 sensors. Thank you. And one of the sensors which it provides is this one with the 2 red lights on. The red lights are just to say it's on, but what is interesting, and I'll leave my glasses just to make sure I get the right program. It's designed for 9-year-olds and not for 90-year-olds. There we go. This is just for a bit of fun, but what it's doing, it's actually measuring where that candle is or where anything is in front of that. So we're right back to where I started. There's Leslie Kay's mobility aid for the blind being used for a Lego robot, and you can sit that and let it run forever. And that allows me to move on to the fun part of this talk, which was to go back to my real origins and the invention of Lego itself and how it reinvented itself and where it's using things which are more than 50 years old. Lego, if you don't remember, started in about 1935 with the manufacture of these little duck toys which you could pull around after you. There's a famous story about that there was a shipment of these things being sent out, and the owner suddenly realized they hadn't had their final coat of paint. He made his son, I think it was, go and fetch all the shipment back and put the extra coat of paint on. He was always concerned about quality. The reason I want to put it up is that we have used this to explore, it has been developed as a method of opening up discussion, and I'm going to illustrate that now by giving you all a little kit of 6 pieces of Lego. And my wife is going to help you out. Try and keep the Lego separate from any food or coffee on your table and from your neighbour's Lego kit. And just look at it for a moment, and I'm going to give you the question in just a second. Right, have you all got one that wants? If you don't want to play, it's perfectly acceptable not to play. All right, you may open the bag, and I'm going to give you 2 minutes, taking the pieces that you've got in the bag to build a duck, just like that duck which you saw. So I've reminded you what a duck looks like. Build a duck. Off we go. I'll set the watch going. Just in case you're timing this, I warn you that I run to a special Lego time, which doesn't bear any relation to any other time. About halfway. Everybody finished it, all right? Anybody else? Are you all done? Are you all done? Are you a chicken? Right? Have a look around and compare your duck with everybody else's at the table. Just have a look. Does anybody have the same duck? Have we got anybody that's got the same duck? Everybody is different. Yeah. The story here is very simple. You have all been given the same set of bricks. You've all been given the same challenge. You've all been given the same time. And you've all built a different answer to the question. And that is a very fundamental engineering point to make. That, you know, I've got how many people in here? 40 people. I've got 40 solutions to the problem. If you want to have a different solution, just get another few people in. In fact, going back to dear Professor Ward, my orthopedic colleague, he used to have a sign in his office. He said, if you want a second opinion, come and see me again tomorrow. Now, I'd like you to put your ducks back in the bag. We would like the ducks back, please. Yeah. You can talk to me later if you really want your duck back. You have to talk to me. The issue is that we are showing you a very simple example of how Lego can be used to explore. I haven't quite finished, if you don't. Sorry. Yeah, I'm getting hand signals. We're using Lego to explore the concepts in your discussion by using metaphors, and you can use the whole system of Lego with specially constructed bits with more complicated questions over a longer period of time to A, have fun together, but B, explore complicated questions. And that is an example of a reinvention of Lego itself. Lego almost failed about 10 years ago and went completely bankrupt. And it reinvented itself. One of the things it did, astonishingly, it started to listen to customers. The other thing is it spread out into many different areas. And this is a little bit of something called Lego Serious Play, which has used something which we often forget about. We went around the institute at the university today and saw laboratories full of computers, full of 3D printers, full of all kinds of things which no longer use the hands. And Professor Kunoff and I were reminiscing over lunch about how disastrous it was that the workshop had been taken away from the Institute of Medical Engineering. And we have forgotten that our hands actually represent an immense amount of what goes on in the brain. This is something which Penfield noticed in 1934. Penfield was the famous neurosurgeon in Montreal who noticed and mapped out the representation of the brain with the hands and said, look, there's a huge connection here. And what we're doing in that very simple example of what we're doing in Lego series play is exploring that, using that, and allowing people to move into new levels of discussion. So, raising the discussion to another level. And that brings us to an end. I hope that's been entertaining. And I would like to thank you for all the ducks coming back. And thank you very much.
On behalf of the Toronto Network, I would like to present a thank you token to Frank.
Thank you very much. All right, there's a way of doing it. Hold it to that. Thank you. That's been a pleasure. It's Lego, all right. Yeah, that's it. Yeah, we'll take these back.
Great, thank you everyone for coming. I believe that Frank will be around a little bit to answer any questions. Okay, if you haven't got a parking validation ticket, Jenny had them. Okay, and if you haven't signed in to let us know that you're here, can you make sure that you do that, just so that we make sure we know who was here. Thank you, everyone. That was fantastic.